All right, so now let's talk about the algorithm to solve this problem, which is sort of for the Dirichlet problem, right? So this is again sort of problems without time dependence, right? Sort of using finite differences. And we're going to focus on the algorithm. Right. So the first observation, if you will, is that if you recall, it's like the defining equation for the problem involves a finite difference stencil, which, if you recall, there's like involves 5 entries, right? So you know basically that every line of it's like the linear system corresponds to an equation involving at most 5 unknowns. Okay, and so as the problem becomes larger and larger, the matrix A, it's like which you're working with, is going to get sparser and sparser, right? So the observation is that right, each row of the matrix A has at most sort of 5 non-zero entries, right? So as n becomes large, right, the matrix gets sparser and sparser. Okay, so in light of this observation, right, it makes sense to implement this method using an iterative scheme. So in view of this, sort of iterative methods for solving this problem, solving this linear system. Sort of AV is equal to B. Okay. So you already know that the known boundary values, right, are Vij, which is equal to Gxi Yj, right, where sort of Xi Yj, right, is equal to I times H, J times H. Right, when, okay, so the known values are when I or J, right, equal to, so equals 0 or n plus 1. All right. Okay. So we're going to solve this. It's like iteratively. It's like by using what is known as the Gauss-Seidel method. So we're using the Gauss-Seidel method. So the Gauss-Seidel method is a fixed point iteration. So let me sort of briefly remind you of how this goes about. So I'm going to write this matrix A as L star, which is a lower triangular matrix with the diagonal, right? Plus U, which is the upper, strictly upper triangular part of the matrix. Okay, so I can write A as L star plus U. Okay, and then with that, you know that A times V is equal to L star plus U times V, but it's also equal to B. Okay, so I have L star of V is equal to B minus UV. Okay, and then L star is lower triangular, so I can easily invert this by using forward substitution, right? So I can get V is equal to L star inverse applied to B minus UV, which is solved, which involves sort of forward substitution. Okay, all right, and this is a fixed point equation because it involves V on both the left-hand side and right-hand side. So the iteration is that Vn plus 1 is equal to L star inverse applied to B minus U Vn, right? And again, the advantage is that if this system is very sparse, it's like this thing is going to converge very, very rapidly, okay? All right, so that's sort of the intuition for all this. So all right, so in practice then it's like what this ends up becoming is the following. So that fixed point iteration ends up looking like the following. So this gives just the following update, that Vij is equal to Vi minus 1 j plus Vi plus 1 j plus Vi j minus 1 plus Vi j plus 1 divided by 4. Okay, so if you recall, that's really just rewriting it's like the defining equation for the finite difference algorithm by solving for Vij. Okay, right. So the way it's set up, if you will, is that you have this. You're actually going to work with this n by 2 by well, n by 2 by n plus 2, sorry, by n plus 2 sort of array, right, of values. But what's happening is that you're only going to update stuff in the interior, right? So the stuff it's like on the boundary is given by the boundary data. I'm going to leave it the way it is. Okay, so that's basically what's going to happen. So even though it's n plus 2 by n plus 2, it's like the stuff on the boundary is coming from the boundary conditions, and then only the interior stuff, which is the unknown, is going to be updated by this Gauss-Seidel type update. Okay. All right. So with that in mind, what you're going to do is you're going to break down the process. It's like into 3 parts, right? So there are 3 parts to this. So the first one is to place the boundary values into the appropriate Vij's, right? And then the second one is to initialize the stuff in the interior, right? So provide suitable starting values for the interior nodes. Then the third part is to carry out m steps of this Gauss-Seidel iteration. Okay. All right, so that's basically what's going to happen. And I'm just going to provide some pseudocode for these parts. So, so for the first task, right, what you can do is that you go from I equals 0 to n plus 1. You do the following. Right, vi0 is equal to gxi0. Vi n plus 1 is equal to gxi1. V n plus 1I is going to be g1 yi, and then v01 is going to be g0 y. Sorry, this is 0i, right? yi. Okay, so yeah, I'm just going to actually use, so what this is basically, what's happening is they're using this index to scan both in the x and y directions, but along the suitable parts of the boundary. So there's some redundancy in this, but it doesn't really matter. Okay, so this is just for the first task. And the redundancy is that sort of the corners get initialized twice, but that's not a big deal. Okay, and then for the third task, let me erase this. This is for task 3. Right, so you have for k equals to 1 to m do. So this is the m steps of Gauss-Seidel, if you recall. So that's the outer loop. And then the inner loop is to scan into the entries, right, from I equals to 1 to n plus, sorry, go from 1 to n, right, and from 1 to n again. Okay, so for j equals to 1 to n do, for I equals to 1 to n do the following, that Vij is equal to Vi minus 1j plus Vi plus 1j plus Vi j minus 1 plus Vi j plus 1, whole thing divided by 4, and the do, and do, and n do. Okay, so that's again very simple thing. You're just updating, it's like everything at once. Okay. Yes, and then that's what you end up getting. Okay. All right, and then it's like you have to choose how to, you know, it's like initialize the interior. There are many ways to do it. You know, one possibility, if you will, is to do, say, something like bilinear interpolation. It's like in the x and y direction, all right? Or just sort of set them to 0. It's like whatever you prefer. And, you know, eventually it's like the method will converge, right? Okay, so so with that, it's like that's the sort of pseudo code, if you will. It's like for the this finite difference based discretization of the Dirichlet problem. Okay, and then the next thing we'll talk about is sort of an approach which is not based on finite differences, but based on sort of shape functions, which is called the Galerkin method. So let me just stop here for now.